Hello and welcome to Physics Platter. Today in Physics Platter we will talk about sound chapter of class 9. In this lecture we will discuss about some definitions of sound, some characteristics of the wave, the mechanical wave that the sound travels in. Okay, so what is sound? Sound is basically a form of energy, as you all know, which creates a sensation of hearing in the ear. Alright, everything that makes sound actually have to have some vibration in it. Without vibration, sound cannot be produced because the vibration produces a wave. Alright, because it's a mechanical wave, that means there must be a vibration in the particles, in the medium particles. We'll talk about that in detail, of course. But for now, to create sound, there must be a vibration. I'm talking because I can vibrate my vocal cord. That creates different frequencies of sound, and that frequency actually travels through the air. All right, and that reaches the ear of the listener, and that's how the listener can hear me. Okay, if you think about the bass, about the speaker, you can also see that the speakers in the loudspeakers, the sound systems vibrate, right? When they are on, they vibrate so much. All right. Okay, so sound is basically a form of energy that creates a sensation of hearing in the ear. Okay, and it propagates from one place to another place in the form of a mechanical wave through a material medium. All right, so we will talk about the wave first. Before going to the sound in detail, we will talk about the wave. What is wave? What is wave? When I tell wave, what comes to your mind first? Of course, the waves in the ocean, right? What is that? That's actually a disturbance in the water. You don't see a wave in the still water. That's absolutely calm, right? You see the waves in the water which is disturbed. So basically, wave is a disturbance in the medium that travels from one place to another place in different forms. Okay, and that disturbance is actually created by the periodic vibration of the particles in the medium. All right, this material wave, of course. Wave can be of two types. So before that, what is wave? Wave is a disturbance that travels from one place to another place. All right, wave can be of two types, of course. First type is the electromagnetic wave. And that it's a wave that does not need any material medium to travel from one place to another place. It can travel even without the material medium. That means it can travel through the vacuum. All right, examples are light wave. Of course, light can travel through the sun to the earth without a medium. All right, it's an electromagnetic wave. Okay, any radiation is an electromagnetic wave. All right, this kind of wave is very, very fast. It can travel very fast. Precisely, the velocity of electromagnetic wave is 3 into 10 to the power 8, as you know. 3 into 10 to the power 8 meter per second. That's the velocity of sound, velocity of light. Okay, and then second type is the mechanical wave. This is the wave that needs a material medium to travel from one place to another place. All right, like sound wave. That means without a material medium, the mechanical wave cannot travel from one place to another place, which also shows that sound cannot travel from one place to another place or cannot propagate through vacuum. Okay, we have a very good example for experiment for that. To prove that, we can take a bell jar. That's very common. Excuse my drawing. That's very common experiment that you can see in every book actually. An airtight bell jar or airtight container, any container actually, which has a bell, something like this, let's say, a bell inside it, which rings if the switch is on. And this container is made in such a way that we can make it, we can take all the air out of it. Okay, that's the system we have here. Now if we switch on the bell or the ring calling bell, let's say electronic bell, when there is air we can hear the sound of the bell, right? Now if we gradually make the inside of the container vacuum, that means if we gradually take the air from inside out slowly, we will see that the sound slowly decreases. Okay, the sound of the bell slowly decreases, and then when it is completely vacuum, we cannot hear any more sound. Although the switch is on and it is ringing, you can see that it's vibrating. This bell is vibrating, of course, but we cannot hear any sound because there is no medium to carry that wave, the sound wave, from the bell, from this part to the surface of the bell jar. Okay, so that proves that the sound needs a material medium to travel from one place to another place. That's why if we talk let's say on the surface of the moon, we cannot hear actually, okay, because there is no air medium to carry the sound wave. All right, okay, so structurally waves are of two types. One is transverse wave, another is longitudinal wave. Transverse and longitudinal. Transverse wave is let's talk about the transverse wave first. Transverse wave. What is transverse wave? That's the most common wave that comes to your mind when we say the word wave. Okay, that means this. Okay, that's the wave that is formed on the water surface. If you throw a stone on the still water of a pond or let's say a swimming pool, we'll see such kind of wave traveling from the middle of the pond to the towards the sides of the pond or swimming pool, right? That's the transverse wave. What is the definition of transverse wave? Before going to the definition, I must tell you one example. Let's say there is a wall here and there is a metallic ring attached to the wall loosely that can move. Okay, and then there is a rope which is also attached to the ring, and the other end of the rope is in your hand. You're holding the other end of the rope. All right, like this. The one end of the rope is attached to the wall through a ring, metal ring, and the other end is held by your hand. All right, now let's say you start moving your hand up and down, just like this. Okay, just like this, you start moving your hand up and down. What will happen to the rope? You will see that because you are moving up and down, the rope will create a structure like this. Like this. And what will happen? This ring will slowly move and then make slow sound, right? Now to move this ring, you of course need some energy. But where did that energy come from? You have applied some force here at the end. You have applied some force at the end of the rope here. But then that energy that you have applied has traveled from your hand towards the wall and hit this ring. Alright, that's why the ring is moving. But your hand was moving in this direction. Look at that. Okay, that means the rope is also moving up and down, whereas the energy travels in the horizontal direction. So such a wave is called the transverse wave, where the particles of the medium or the source moves perpendicularly to the direction of propagation of the energy. Alright, such a wave is called the transverse wave. I repeat, transverse wave is a wave in which the particles of the medium vibrate perpendicularly to the movement of the propagation of the energy is called the transverse wave. Or in another way, we can say that the movement of the particles and the propagation of energy are perpendicular to each other in case of the transverse wave. All right, we give another example. Let's say you throw a stone. You throw a stone in the pond somewhere here. All right, and then the water created a wave like that towards the shore. It slowly moved towards the shore. All right, such a wave is called the transverse wave. Now let's say if there is a piece of paper floating on the water, what will happen to the piece of paper? You will see that the piece of paper is moving up and down, right? It moves slowly up and down with the wave, of course. But will that, if there is no air, will that paper move towards the shore as well with the wave? No, it does not. It moves in the same place. Well, that's a very important characteristic of a wave. In a mechanical wave, the particles of the medium does not permanently shift from one place to another place, or does not have a permanent displacement in case of the mechanical wave. All right, permanent displacement of the medium. All right, through the wave only the energy travels, not the particle mediums. They remain in the same place. They move to and fro or up and down around a mean point, which is the middle of the movement. It goes up and the same distance down around a point, and that point is called the mean position. Mean position of the particle, topmost the peak position, top and bottom the peak positions. All right. So in this case, the vibration of the particles are perpendicular to the propagation or direction of the propagation of the energy, transverse wave. Okay, there are some terms involved with the transverse wave. Let's talk about them now. Let's draw a transverse wave first. Okay, 0, graphically we can represent it like that. This is time t, and this is the displacement, which is not permanent, of course. It goes up and down of the particles. Okay, so the maximum height reached by the particles, material particles or medium particles, are called the peak points. Okay, the topmost peak point is called the crest of the wave. The bottommost point is called the trough. Crest and trough. The topmost is the crest, the bottommost is a trough. All right. Okay, now there is something called phase. What is phase? Phase is basically nothing but the term or the quantity that represents the state of the motion of a particle. Any particle actually. Just with the phase you can say where the particle is, what's the velocity, or in which direction the particle is moving. Okay, so it is just the state of motion. State of motion of the particles. So if we say that in this part, what is the state of the motion? Phase is along this direction, because the particle is moving along upwards. This also upward, this also upward, this also upward. This is at rest, and then from there downwards, because the particles are moving downwards now. Downwards. So these are the phase now. At this position it comes to rest again and then reverses the movement. All right, so that's called the phase. All right, so phase is the state of motion of a medium particle in case of this. Remember that in this case we are only talking about the material mediums, because we are talking about the sound waves. So we will talk only about the material mediums for now. We'll talk about the electromagnetic wave and the other waves later when we talk about these things in the higher classes 11 and 12. All right. Okay. So that's the phase. Now something called the complete vibration. Complete vibration or complete wave. What is the meaning of complete wave? A complete wave is if we take the part of the wave between two consecutive particles with same phase. Part of the wave between two consecutive particles with same phase is called the complete wave. That means if we start from the crest, it moves all the way down and then it goes to the next crest. There is also crest, of course. Then a complete wave is completed. One wave is completed. All right, crest to crest. Or if you start from this position, let's say, where is the next particle? In this, if we come to this, see here, this was downwards, this is upwards, so this is not the case. So somewhere here will be the next particle. All right, with the same phase. So from this position to this position. Also, if we take the trough, from the one trough, two consecutive troughs. One trough to another trough, or one crest to another crest. That's a complete wave. Am I clear? All right. Now, the wavelength. What is wavelength? Wavelength. Wavelength is the distance between of a complete wave. Complete wave. What does it mean? It is the distance between two consecutive crests, or basically more precisely or more generally we can say the distance between the two consecutive particles with the same phase is called the wavelength of a wave. All right. So this distance from crest to the next crest is called the wavelength. The wavelength is represented as lambda. The SI unit is meter. Simply it's a length, so SI unit is meter. All right. So wavelength is the length of the distance between two consecutive particles with the same phase, or you can more easily you can say that, maybe it's easy to remember that the distance between two consecutive crests or two consecutive troughs is called the wavelength. It's represented as lambda. The SI unit is m. All right. Okay. Now amplitude. Amplitude. What is amplitude? Amplitude is nothing but the maximum displacement of the particle from its mean position. So this line is the mean, represents the mean position. So this is the amplitude, or in this direction, this is the amplitude. Okay. Remember one thing, this is the maximum displacement from the mean position. All right. So you have to take the distance traveled by the particle in only one direction, not in both the directions. All right. The particle in one direction only, because if you talk about the total displacement of the body, it's zero, because it's going the same distance in both the sides. So total displacement is zero, right? So only in one direction the maximum displacement of the particle is called the amplitude of the particle. All right, or rather the distance of a crest or a trough from its mean position is called the amplitude of the particle, of the wave. Represented as a, SI unit is again meter, because it's again a distance only. Okay. Then frequency. Frequency of the wave, represented as nu or f, I prefer nu. You can represent f as well. You will see there are so many books that represent frequency as f. So represented as nu. SI unit is numbers per second, or simply S inverse. S is for second, or hertz. They are similar. Number per second or hertz. What is frequency? Frequency is basically nothing but an event, the number of events that happens in 1 second is called the frequency. Alright, number of events that happens in 1 second. In another way, in this case we can say that the number of complete waves, complete vibrations of a particle in 1 second is called the frequency. Number of complete vibrations in 1 second is called the frequency. So nu is the frequency. Alright, complete vibration means what? To represent the complete vibration, we can also give an example of a simple pendulum. The pendulum travels, oscillates like this. So if it starts from A, it goes to O and then goes to B and then comes back to A. That's the complete vibration of the particle. Alright, and if a particle is moving in this direction, let's say something like this, O, A, B, then if the particle starts from A, it goes all the way to O to B and then comes back to A, and then we say that the particle completed one full vibration. Okay, such full vibrations, number of such full vibrations in 1 second is called the frequency. All right. Okay, time period. Time period represented as T. SI unit is simply second because it's a time. So time period is the time taken by the particle to complete one full vibration. Time to complete one full vibration is called the time period, represented as T. Alright, now if we consider the T means what? Number of, it's one full vibration. That means we can say that if there are n number of vibrations happening in t seconds, let's say t seconds, just for example, let's say a particle is vibrating and there are n number of complete vibrations happening in t seconds, then what is the frequency and time period of the particle? So if n number of vibrations happening in t seconds, let's say, so in t seconds we can say that n number of vibrations happening in t seconds, that means one vibration will take time t minus n, and thus that will be the time period of the particle. Alright, if the particle is moving n complete vibrations in t seconds, then in 1 second the particle will move t by n. In one vibration the particle will, to complete one vibration the particle will take the time t by n, and that is the time period. That's the definition of the time period, and that is represented as t. So we can say t equals to t by n. Alright, now another way, t seconds, in t seconds there are n vibrations, right? So therefore in 1 second how many vibrations will there be? N by t. Alright, and that is my frequency, because number of vibrations per second is called the frequency. So lambda equals to nu equals to n by t. Okay, from there we can say that nu equals to n by t equals to 1 by t. That means the frequency is the inverse of the time period of the particles. Alright, frequency is the inverse of the time period of the vibrating particle. Okay, so that these equations might be useful to solve the problems. We'll solve the problems later. Okay, so that's our time period. What else? Now the velocity of the, before that, okay, let me complete the wave first and then we'll talk about sound in detail. Okay, velocity of sound. Velocity, of course, represented as V, and the SI unit is meter per second. What is the meaning of velocity? Velocity is the distance traveled or displacement of a particle in 1 second, right? In unit time, basically. So, displacement or distance traveled by a particle in 1 second, right? If the wavelength of the particle is, let's say wavelength is lambda, frequency equals to nu. Now let's say wavelength is lambda. What does it mean? Means one complete distance of the one complete vibration is lambda, right? Let's say, let me draw it again. So this is lambda, right? That means lambda is the distance traveled in t. If the lambda is a wavelength, in how much time does it take, does a particle take to complete one wavelength, one complete wave? Time period t. Time period t. Right. So lambda distance, it travels lambda distance in how many seconds? T seconds. Right, or rather we can say that in t seconds the particle moves lambda distance, because that's the wavelength of the particle. Therefore, how much will it travel in 1 second? That will be the velocity, right? Therefore, in 1 second the particle moves lambda by t meters. If this is meter, this is also meter or centimeter or kilometer, whatever you take. Okay, but you have to take all the things in one unit only. Okay, anyway, so t seconds the particle moves the wavelength distance, which is lambda distance. Therefore, in 1 second the particle will move lambda by t distance. Therefore, that will be the velocity of the particle, lambda by t. Right? What is the velocity? Velocity is the distance traveled by the particle in 1 second, and in 1 second the particle moves lambda by t distance. Therefore, v equals to lambda by t. Now 1 by t, we can say lambda into 1 by t, or we can say lambda into nu, and this is very important equation. This is very important equation. V equals to nu lambda, velocity of sound, velocity of anything actually, that any wave actually is nu lambda. Okay, all right. In 0 degree centigrade temperature, at 0 degree centigrade temperature and 76 centimeter of mercury pressure, the velocity of sound Vs equals to 332 meter per second. All right, this is experimentally found. At 0 degree centigrade temperature and 76 centimeter mercury, the velocity of sound is 332 meter per second. Why do you have to mention the temperature and pressure? Because the velocity of sound changes with the temperature and pressure. All right, basically the velocity of sound increases with the temperature. More precisely, the velocity of sound is directly proportional to the square root of the temperature of the of air. This is of course in air. All right, and of course the velocity of sound in solid is the maximum, is more than the velocity of sound in liquid, and that's even more than the velocity of sound in air. They are different. These for air, they are different values, and that's very important thing to remember. Velocity of sound in solid is more than the velocity of sound in liquid. That's more than the velocity of sound in air. All right. Okay. Now we'll talk about the other form of wave, another wave which is called the longitudinal wave. Longitudinal wave. In this wave, the vibration of the particle and the propagation of the energy are parallel to each other. Okay, that means the direction in which the particles vibrate and the direction in which the energy propagates are parallel to each other. Example, of course, if we, let's say, tie a spring, just like rope in the previous, in case of the transverse wave, if we tie a spring, attach a spring to the wall, and then the other end is free. Now if we stretch the other end to some distance and then stretch the spring and then let's say leave it, then what happens? The spring vibrates like this, right? And of course it hits the wall. That means the energy is traveled from this towards the wall in this direction, and the particles also are vibrating in the parallel direction, in the horizontal direction. That means they are parallel to each other. In this, such type of wave is called the longitudinal wave. Examples are spring, of course, and then the sound wave. In case of transverse wave, we have seen that the consecutive crests and troughs are traveling through the wave. In this case, consecutive compression and rarefaction are propagating through the wave. All right, compression and rarefaction. What it means? Have you seen some insects moving like this? Let's say like this, right? Some insects move like this. They first compress their body and then expand, then compress again and then again expand their body, and this way they travel. They're propagating actually from one place to another place, right? So this is a very good example of the longitudinal wave, compression and then the expansion of rarefaction. All right, compression and rarefaction of the medium. All right, so in case of the air, how does it look? The compression is actually the air is compressed first and then it expands, and then it expands, and then it again compresses and then again it expands, and this way the energy propagates from one place to another place, and that's called the longitudinal wave. All right, just like the transverse wave, this is compression, this is this is compression, rarefaction, compression. Just like the transverse wave, in case of the longitudinal wave, the wavelength is defined as the distance between two consecutive compressions or two consecutive rarefactions. That's the wavelength of the longitudinal wave. Okay, this kind of wave, that means longitudinal wave, is only material wave or mechanical wave. Remember that, because compression and rarefaction happens only in case of the material medium. All right, so electromagnetic wave cannot be longitudinal. Only mechanical waves like sound, spring are longitudinal waves. All right, so sound wave is a longitudinal wave that has compression and rarefaction in the air, and it travels through the air in consecutive compression and rarefaction. Compresses, expands, and in this way it travels, it propagates from one place to another place. All right, so these are the waves. The wave part we have discussed here is complete. In the next part we will discuss about the sound. All right, okay, for now this is good enough for today's lesson. In the next lecture we will talk about the sound. All right, some characteristics of the sound and some terms involved in the sound. All right, so see you in the next video very soon. Till then, take care.